Let's begin notes 10.3, area of regular polygons. A review of regular polygon. We know that a regular polygon has all sides and angles congruent. All the sides are the same length, all the angles are the same size. Let's have talk about some vocabulary for our regular polygons. First of all is the idea of the center of a regular polygon. It's the center of a circumscribed circle. What do we mean by that? And you'll see this point right here is the center. If we were to take that point and make a circle with a radius that went from that circle to one of the vertices, that circle would circumscribe the regular polygon, or more common words, it's going to make a circle that only touches the regular polygon at all of the vertices. In this example, we have a hexagon, so it has 6 points that are on the circle. If it were an octagon, it would have 8 points on the circle. A decagon, 10 points that are on the circle. And that's the idea of circumscribing a circle. The next term we have is a radius. And now you might recognize that these terms are the same terms as terms we use with our circle, and they have that same meaning. So a radius is the distance from the center to a vertex. Now, of course, with a circle, we have all the points on the circle. That would be the distance of a radius. In this example, this length here is a radius. You can see there are 1, 2, 3, 4, 5 others for a total of 6 radii on this regular polygon. Of course, if it were an octagon, there would be 8, decagon 10, and so on. Unlike a circle where there's an unlimited number of radiuses that you can draw. Let's talk about our next term, which is a brand new one. It's called an apothum. Apothum sounds like possum. Apothum. Apothum of a regular polygon is the perpendicular distance from the center to a side. Not just anywhere on the side, but perpendicular distance to it. In our example here, the apothum is shown by this length. It goes from the center and then intersects the side. There's an apothum for this side. We could do the same thing for this side, and so on a regular polygon. The apothum would be the distance from the center that's perpendicular to that side. There can be only one drawn to each one of the sides. Okay. Now, what we're going to go through real quickly is looking at some of the angles that are created inside of a regular polygon. They're going to be very useful for what we're going to do today. So take a look below. You'll see that we have a regular polygon here, that's a triangle, an equilateral triangle. All of these sides are congruent. This one is a regular quadrilateral. A regular quadrilateral is actually a square. All of these sides are congruent, and all of these angles are congruent, so therefore they must be 90 degrees. Then we have our regular hexagon, similar to what we have up here, and also a regular pentagon, 1, 2, 3, 4, 5 sides on those. Okay. So what we're going to do is we're going to look at the central angle. We've talked about these before. The central angle is right here at the center, same center that we talked about above, and the central angle is drawn by drawing each one of these radii. Radii go from the center to the vertex. We have 1, 2, 3. In the triangle, we have 1, 2, 3, 4. In the quadrilateral, and you can see the pattern here, 6 in the hexagon, and 5 radii in the Pentagon, which helps us calculate the central angle. The central angle is real simple. You can see we've done this before. We find the measure of the central angle by taking 360 and dividing it by the number of sides, because the number of sides give us the number of central angles. We did this last unit when we were rotating things in a regular polygon. So this one, you can see there are 3 central angles. We're going to take 360, divide it by 3, and get 120 degrees. In the hexagon, 1, 2, 3, 4, 5, 6 of these. So to find this central angle, we'll take 360 and divide it by 6, and that'll give us 60 degrees for each one of those. In the regular quadrilateral or square, we'll have 4, so we'll take 360, divide it by 4, and that gives us 90. We know that each one of these are 90. And if you recall, we did, when we studied quadrilaterals several units ago, we did talk about the fact that the diagonals of a square will always be perpendicular to each other. And this kind of proves it. Next, we have our pentagon. 1, 2, 3, 4, 5 central angles. 360 divided by 5 will give us a 72-degree angle. Each one of these angles are 72 degrees. Nothing new. We've done this before. Now let's move on to the next diagram. The next diagram takes what we just did, and we're going to take one of those central angles, and we're going to draw a line from that vertex of that central angle that's perpendicular to the side. That creates a radius. This is the same radius that we had up above. This length here that's drawn is a radius. And we're going to look closely to the angle that it creates in here. We'll see when we draw this, this always takes the central angle and splits it in half. We created a 120-degree angle here when we drew the radius, and now we're going to split that in half and get this angle here 1/2 of 20, or excuse me, 120, which gives us a 60-degree angle. Let's take a look at the hexagon. From up above, we know that each one of our central angles are 60 degrees. Angle 2 is this angle here. Angle 2 is 1/2 of 60, or 30 degrees. That angle there is going to measure 30 degrees. Let's move on to our next one. In this one, we have a square, and the square, remember, had a 90-degree angle there. Our angle 2 is going to be 90 divided by 2, or a 45-degree angle. And you can see it's really straightforward and something to help you. We're going to keep calling this angle 2, angle 2, angle 2. That helps remind us that to find that, all we have to do is take our central angle and divide it by 2. Central angle, 72. We already calculated it here. We'll take 72, divide that by 2, which will give us 36. And that means that that angle there is always going to be 36 degrees when we have a pentagon. We're going to move on to the next page. And in the next page, we're going to look at another angle. We started off with our central angle. If we wanted to, we could have called that angle 1. Then we looked at angle 2 here. And in our next one, we're going to look at another angle in this regular polygon, which we're going to call angle 3. And that's in this corner here. If we look at this triangle, you'll see that from what we did previously, this angle was 1/2 of our central angle, angle 2, and that was 60 degrees, 120 divided by 2. We look at this triangle. I'm going to redraw it over here. This is a 90-degree angle. This is a 60-degree angle. All of these need to sum to 180. So we'll take 180 and subtract the 90 plus 60, which will leave us with a 30-degree angle. Angle 3 is 30 degrees. And we'll repeat that same pattern with each one of these others. From our previous problem, we found this angle was 30. Half of 60 gave us angle 2, which means we're 60 degrees away from getting 180 degrees, so angle 3 is 60 degrees. In the next one, and this right angle doesn't show up very well, but remember this was a 45-degree angle, the central angle. We're looking for angle 3. 45 plus 45 plus 90 gives us 180, so angle 3 is going to equal 45 degrees. Next, let's move on to the Pentagon. In the Pentagon, as you recall, we did get an angle here, angle 2, of 36 degrees. So we're going to have to take 180 minus the 90 minus 36, and that will give us a 54-degree angle for angle 3. And we're going to use some of these angles as we go into the next part. And this next part is very important for us to just follow the procedure. We're going to calculate the area of regular polygons. This formula kind of looks a little bit familiar. It's got a 1/2 in it, and then it's got two numbers that we're going to multiply together. It's going to be 1/2 lowercase a and capital P. If you remember from geometry, we always use capital letters for things that are calculated. A formula is going to be needed to get one of these. And lowercase letters for something we can go right to the diagram and take off of the diagram. In the diagram, you'll see it's trying to point out what these two things mean. We use A for the apothem. Remember, that was that new term we just went over. Apothem is the distance from the center of the regular polygon to one of the sides and is always perpendicular to it. And one thing I didn't mention is no matter what apothem we choose, they're always going to be the same length. Okay? So there's not going to be different sizes of those. And then the capital P is our good old buddy perimeter. Okay? Remember, perimeter is the distance around. Start here and walk all the way around, adding up all the lengths of the sides. When you get back to here, you have your perimeter. So let's go ahead and do this one in our first problem. You'll see these are kind of split up with similar shapes, or not similar shapes, but regular shapes with similar information given. The first three, in each one of these, we have the apothem given to us and a side. These are going to be the easier ones to get, because if we look at our formula, area equals 1/2 A times P, well, they gave us one of the numbers that we need to use. They went right ahead and said the apothem is 6.9. So in our formula, 1 point, substitute, we're going to just substitute in 6.9, and then all we have to do is put in our perimeter. And our perimeter is not 8. Remember, perimeter is the distance around. A side is not the distance around. Now we could go 8 plus 8 plus 8 plus 8 plus 8 plus 8, but we know the easier way to find perimeter is, since all of these are all the same, and we know it's a hexagon, we'll just take 8 times 6, and that will give us our perimeter. Just put all this in our calculator, we'll get 165.6 meters squared. Let's take a look at our next one. Area equals 1/2 A times P. Our A value is again given to us. Don't have to worry about doing any calculations for that. We're just going to do area equals 1/2, in this case 2.9, and then our perimeter. 10 is the length of one side. We can see that it's a triangle. 10 times 3 will give us 30, and then we'll just take these numbers, put them in our calculator. If you want to do 1/2 of 30 before you put it down, I think That's an easy one to do. 15 times 2.9. Put that in our calculator. We'll get 43.5 meters squared. In our next one, we still have a regular polygon with two pieces of information given to us that we like. The apothem and one of the sides. The apothem is this distance here from the center, perpendicular to the side, which is given as 5. Area equals 1/2 of 5 times our perimeter of 10. 1, 2, 3, 4. 4 times 10 gives us 40. Let's do half of 40. Half of 40 is 20. 20 times 5 will give us an area of 100 meters squared. Pretty straightforward. We like it when they give us our area. The only thing we need to calculate is the perimeter by taking the length of one of the sides times the number of sides, times 4 in this case, times 3, times 6. Obviously, if it were a hexagon, or a pentagon, we would do times 5, a decagon times 10, and so on. Let's move on to our next set of problems. Our next set of problems, the writer of the problems wasn't as generous as this one. You'll see in each one of these, they don't give us the apothem. All they give us is the length of one of the sides, which does make perimeter nice and easy for us to calculate. I'm not going to fret about that. I kind of like that idea of giving me at least one dimension that I can quickly find the lengths of. So let's look at this. We've got area equals 1/2 A times P. P is pretty straightforward. 1, 2, 3, 4, 5, 6 times 10. That we know is going to be 60. But the apothem is something we're going to have to work at getting. Okay? Let's go back to what we did to start this. We looked at this hexagon, and we first found a central angle. The central angle here was 360 divided by 1, 2, 3, 4, 5, 6. 6 sides, 6 vertices, 6 central angles. 36 divided by 6 gave us 60. And then let's hone in on this angle right here. This one was the angle we called angle 2. And we use that to help us remember that all we have to do is take this central angle of 60 degrees and divide it by 2, and that gives us 30 degrees, and that's the measure of angle 2. Now, look closely. When the apothem is drawn here, the length that we need for our formula, that A, it intersects one of the sides and splits it into 2 equal parts. It's always going to land at a midpoint, which makes a quick calculation. Half of 5, or half of 10, we get 5 for that length there. Now, I want to look at this shape here. I'm even going to redraw it for us right over here. This is the apothem that we're looking for. That's this length here. Angle 2 was drawn right here of 30 degrees. That was half of our central angle. And then we just found half of the side. This length here is 5. And now you can see we end up with a right triangle, one side given to us and a length, which means we're going to go right back to our good old SOHCAHTOA. Our steps, right SOHCAHTOA at the top. Next, shade in the angle. This is the 30-degree angle that we found. Angle number 2, half of the central angle. Label what we know. We know 5 is the opposite side. And A is not the hypotenuse, but is the adjacent. OA gives us a tangent problem. That means the tangent of that 30-degree angle will equal opposite 5 over the adjacent A. Writing it as a proportion, you can see that we're not going to bother using our calculator for the multiplication and the cross multiply, but we are going to use our calculator for the divide portion of it. So our apothem is going to be 5 divided by the tangent of 30, which gives us 8.66. We'll take that value and put it in our formula, and this should give us 259.8 meters squared. Let's try another one. Same thing given, only the length of the side. Area equals 1/2 the apothem times the perimeter. We need to calculate this apothem. Perimeter is pretty straightforward. 12, 12, 12. 12 times 3, which gives us 36. But let's go back again. This is the apothem. That's the length that we need. That's going to give us this right here. We know that we have an angle 2 here. Angle 2 is half of our central angle. So let's go back and look at the central angle. It's this guy. That was 360 divided by 3, which was 120, which means angle 2 is going to be half of 120, or 60 degrees. Like we did before, we have half of the side going from that vertice to where the apothem ends. Half of 12 gives us 6, and we again have another right triangle with a 60-degree angle this time as the central angle. The apothem is here, and the side of the triangle is 6. So let's use our SOHCAHTOA again. Shade our angle. That's a 60-degree angle. We're shading that in. 6 is opposite. Angle 2 is here. A is adjacent. Now, I want to point out before we write our ratio here, the nice thing about the way these problems are being set up is we know that we're calling this angle 2 to help remind us that all we do is take the central angle and divide it by 2 to find that angle. If we choose angle 2, the apothem is always going to be A, the adjacent side. Every time we draw an apothem and look at this angle, which we've called angle 2, the apothem is going to be A. A for apothem, A for adjacent. It makes it really simple to memorize how to do these problems. So again, we have another tangent problem. The tangent of 30, or excuse me, this time 60, will equal 6 opposite over A, the adjacent. The portion is going to be, again, like we did before, easy multiplication, division with the calculator. A equals 6 divided by the tangent of 60. 6 divided by the tangent of 60 is about 3.4. So we'll use 3.4 for our apothem, and we got it made. Just go right to our calculator, put all those values in, we'll get 61.2 meters squared. Done. Okay? We're going to continue on. There are 2 more types of problems. We had our first problem, which was given the apothem and a side. We love that one. The only hard calculation we did was just the length of the side times how many sides. Then we shifted to the last set, where they gave us the length of the side. Thank you. 1, 2, 3, 4, 5, 6 times 10. 12 times 1, 2, 3. That gave us the perimeter. That part of the formula was easy, but we did need to use SOHCAHTOA to find the length of the apothem. The next set of problems you'll see in each one of these, we're given our apothem. So, hey, that doesn't sound too bad. 1/2 area, or the area is going to be 1/2 the apothem times our apothem. This is just going to be 1/2 of the apothem that's given to us of 3, and all we need to do is our perimeter. But you'll see they didn't give us a length of the side. To find the perimeter, we're going to have to do some calculations, and it's the same type of calculations we did already before. We're going to go right here to good old angle 2. Central angle, we did it up here, 60 degrees. 360 divided by 6 gave us 60. Angle 2, this guy right here, is going to be half of 60, 30 degrees, which gives us another right triangle. And this guy in here is a right triangle. The apothem given to us is this length. What we need to do is find this length of that right triangle. Go right back to SOHCAHTOA again. We're given this time, again, we've got SOHCAHTOA written at the top. Let's shade our 30-degree angle. 3 meters in this case is adjacent, and that's our apothem. Remember what we talked about up here. Apothem's always going to be the adjacent. And what we're looking for, we'll just call this length x, that is opposite the 30 degrees, or again, with a tangent problem. In this case, the tangent of 30 degrees equals opposite x over the apothem, the adjacent, which is 3. As a proportion, you'll see this time it's going to be the multiplication we're going to use on our calculator. Cross multiply, divide by 1, no need for a calculator. This will give us 3 times the tangent of 30. 3 times the tangent of 30 is 20. Oops, I'm sorry. Let me check my calculations here real quickly. It is 1.7. Looking at the wrong problem. Yeah? Let's try this again. 1.7. Just a little bit off of that. So 1.7 is this length x. I want to remind you where we got that. That is half the length of this side. So we've got to remember that x is not the whole length of the side. The length of the side is going to be, this side here is going to be 2 times 1.7, or 3.4 meters long. This side is 3.4 meters long. So to find our perimeter, we're going to have to take 3.4 and multiply that by 6 in this case. 3.4 is the length of the side. Double the 1.7 that we got here for x. 1.7, 1.7, 3.4 for the side. Multiply that by 6, and we get a perimeter of 20.4. Boom. Put it in our formula, and now we got it made. Put it in our calculator. Half of 3 times 20.4 will give us 30.6 meters squared. Let's do another one just like that, except instead of doing the hexagon, we'll just use our regular triangle here, the equilateral triangle. Same thing, area equals 1/2 A times P. The A is given to us, the apothem, of 9 meters. That's this length right here. We'll go right back to what we've done before. Okay, follow this procedure. Keep it simple. Central angle, 360 divided by 1, 2, 3, 120. Angle 2 is half of the central angle. Angle 2, half, divided by 2. That gives us 60 degrees for this angle. Next, we're looking for this length here in the triangle. That length there we're going to call x. SOHCAHTOA. We have it written all the way back up here at the top of our paper. Shade, the angle that we know. The side that we know is adjacent to it. It's the apothem. Apothem, if you're choosing angle 2, will always be A. X is opposite that. Same thing we had before. O and A, a tangent problem. TOA. Tangent of 60 equals the opposite x divided by 9. Cross multiply, divide by 1. X will be 9 times the tangent of 60. X is going to be In this case, let's just round it to 7.8. And don't fall into the trouble of putting that in for P. It's not P. It's not even the length of the side. The length of our side is going to be double that, 15.6. That's the length of the complete side, double the value we got for x. That's still not our perimeter. Our perimeter is going to have to be 15.6 times 1, 2, 3. 3 sides this time. And that gives us a value of 46.8. And that's what we're going to put in for our perimeter, 46.8. This, of course, still was the 9 that we were given. Put that in our calculator. And, oops, yeah. I think I got some wrong numbers here. I'm sorry, I'm looking at some wrong numbers. Let me quickly go back. Right here, I think if you check your numbers, this value should have been 15.5. Sorry, I'm looking at the wrong problem. This one's 15.5. 15.5 is x, which means when we double that, the length of our side is going to be 31. 15 and a half times 2 is 31. So we're not going to use 15.6 times 3. We're going to use 31 times 3 to give us a perimeter of 93 meters. And that's what we're going to substitute in here. This is 93. I apologize for that. Okay. So again, just quick change here of a few numbers. And then when we put it in our calculator, we'll get 418.5 meters squared. We've got 2 more to do. In this case, they don't give us the length of the side. So we can't just multiply it by 3 or multiply it by 4 and get our perimeter. They don't even give us the apothem. This one's going to take a little bit more work in order for us to get the 2 values we need in our formula, the apothem and the perimeter. So let's go back to what we have here. You can see that we're given the radius. Central angle, 360, divided by 3 is 120. Angle 2, half of that, 120 divided by 2 gives us 60 degrees for this angle here. We want to know the apothem. SOHCAHTOA all over again. This time, what we know, here's our angle, is not the opposite nor the adjacent. What we know is this length here, which is our hypotenuse, which is h. A is getting easy for us. The apothem is adjacent. Now we have a and an h problem, which is our ka in the SOHCAHTOA. So to find A, the apothem, we're going to do this angle here. The cosine of 60 degrees equals A over h, the apothem over h, which is 9. Write it as a proportion. This one's going to be multiply in the calculator, and of course cross multiply and divide by 1 will be nice and easy for us. So A, the apothem, is going to be 9 times the cosine of 60. 9 times the cosine of 60 gives us 4.5. All right, we're halfway there. We've got half of the numbers that we need. We've got 4.5. What we need is now the perimeter. To find the perimeter, now that we know the apothem, we want to find x, this length right here. How are we going to find that? Go right back to SOHCAHTOA. We're given the hypotenuse, already have that marked off here, but now we want x. X is opposite, so ignore the A over here. We're now dealing with O and H, which means we're now in a SO, the SO portion of the SOHCAHTOA. So let's write our proportion here. This is going to be the sine of 60 degrees equals opposite x over the hypotenuse 9. So x is going to be 9 times, not the cosine, not the tangent, but the sine of 60 degrees. 9 times the sine of 60 degrees will give us 7.8. This, again, is not the length of the side. It's actually half the length of the side. The length of our side from here to here is going to be double the 7.8. Length of our side is going to be 7.8 times 2, or 15.6 meters long. The perimeter is going to be 1, 2, 3 times that. 15.6 times 3. 15.6 times 3 should be 46.8 meters long. That's the value we'll put in here in our formula and in our calculator and calculate 105.3 meters squared for the area of this regular polygon. We got one more to do. Same thing as we did here. Our fourth type of problem, where they only give us our radius. We're going to have to use SOHCAHTOA twice to find our missing values. So just take your time. We're going to look again at this triangle right here. Same process we've done before. Start with central angle. Central angle, 360 divided by 1, 2, 3, 4 sides, 4 central angles. That gives us a 90-degree angle here. This angle is going to be our angle 2, which is half of 90, or 45 degrees. We need the apothem, and we need x. The apothem is this length here, and x is this length here. So we'll go to our good old SOHCAHTOA process, shade the angle. The hypotenuse is 5. The adjacent is apothem. So isn't that nice again that the apothem is always adjacent, which gives us the cosine. Remember, the ka in the SOHCAHTOA is cosine of 45 equals the adjacent a over h. That gives us 5. Cross multiply. This will be apothem equals 5 times the cosine of 45 degrees. 5 times the cosine of 45 gives us 3.5 meters long. So our formula, area equals 1/2 A times P, will be 1/2 3.5 times our perimeter, which is going to come from x. X is opposite, so this ends up being the SO of SOHCAHTOA. The sine of 45 equals x over 5. So we'll do x equals 5 times the sine of 45. 5 times the sine of 45, believe it or not, gives us 3.5. And we should have expected that, because this has to be a 45-degree angle also, which means we have an equal isosceles right triangle. 3.5 is not the length of the side, it is x. To find the length of the side, we'll double 3.5 and get 7. We'll find the perimeter by doing 7 times 4, which gives us 28. Put that in our calculator, and we will get 49 meters squared for the area of that regular polygon. And that concludes 10.3. Go ahead and proceed to your homework.